We are students and postdocs at the University of California, Berkeley. Our project is titled Solving the Arsenic Problem in Rural California. Arsenic in drinking water is a problem in many parts of the United States. In California, over 55,000 people rely on public water systems that have arsenic concentrations above the EPA's maximum contaminant level of 10 micrograms per liter. The arsenic problem has been cited as an environmental justice issue, with the majority of out-of-compliance systems serving poor, Latino, and African American communities. With the interrelated issues of climate change, drought, and overpumping, a sustainable technological intervention is required to meet the needs of those communities exposed to high levels of arsenic. In addition to being a carcinogen, arsenic exposure causes skin lesions, ulcers, and gangrene, as well as cardiovascular, neurological, and immunological diseases. In our project, we have 3 objectives. The first is to demonstrate arsenic removal from very high initial concentrations of 1,500 micrograms per liter to below the EPA maximum contaminant level. The second objective is to design and optimize a compact, stacked continuous flow system that produces 600 liters per hour of arsenic-safe water. Meanwhile, we are developing a partnership with the community exposed to high levels of arsenic in the groundwater in rural California. Finally, the third objective is to conduct a first-order economic analysis to estimate the total cost of a community-scale plant in California. In our lab, we are developing a technology called ACAI, which stands for Air Cathode Assisted Iron Electrocoagulation. ACAI is a rapid, compact, and affordable technological innovation for effective arsenic removal from contaminated groundwater. In ACAI, we electrolytically dissolve an iron anode in an electrochemical cell to form iron precipitates. By employing a carbon-based air diffusion cathode, we also induce the oxygen reduction reaction to produce large amounts of hydrogen peroxide. In the process, arsenic-3 is oxidized to arsenic-5, a more readily adsorbed form of inorganic arsenic. The arsenic-laden iron sludge is then settled out, producing arsenic-safe drinking water. Our next steps are to complete the testing of a 600 liter per hour ACAI continuous flow system. Subsequently, with support from our community partners, we will conduct a field test of ACAI in the Central Valley of California. During the field test, we will collect user feedback from the community and system operator. We will also iterate the design of the system and retest. We plan to conduct a higher resolution cost analysis and confirm the feasibility of ACAI. Finally, we will redesign the system from economic and community feedback and test the system for remote monitoring. Thus far, we have demonstrated that ACAI removes 1,500 micrograms per liter of arsenic to levels much below the EPA MCL. We have also designed and built a 2 liter per minute flow-through ACAI reactor module that is robust, capable of operating at high throughput, and is leak-proof. At scale-up, this modular design will produce arsenic-safe drinking water at a rate of 600 liters per hour. Our initial cost assessment indicates that ACAI can be an affordable solution to residents of rural California. In the long term, this technology can reduce the number of arsenic-related diseases, thus lessening the burden of disease and increasing economic prosperity in communities that must currently rely on arsenic-contaminated groundwater.